Stephen Hawking wants big answers to big questions.
How can we understand the universe? Is it arbitrary, or is there a grand design? Do we still need a God?
In 1988, Stephen Hawking wrote an unlikely but sensational bestseller and became an instant celebrity. In the book, he promised we would soon have the ultimate answer, a theory of everything that explained how the universe began. This film tells the story of what happened next, Hawking's 20-year struggle to fulfill his dream and the extraordinary events of his personal life. Today, almost completely paralyzed, Hawking is tantalizingly close to his goal. It seems that he and his fellow physicists may be about to discover the secret of the universe's beginning. Stephen Hawking's record-breaking best-selling book, A Brief History of Time, has made him an international celebrity. But time is precious to a man who clicks out sentences at 3 words a minute. Hawking was diagnosed with motor neuron disease in 1963 when he was a PhD student. Doctors gave him 2 years to live. For 40 years, he's defied their predictions. With a string of major discoveries to his name, he's become the world's most famous scientist. But being a celebrity can have its drawbacks.
This is our fans, Professor Hawking's fans, huge, incredible piles of mail. Their imaginations are extremely interesting. You get people who write in about time wormholes and about spacecraft, alien invaders, teleporting. How can Professor Hawking possibly comment on all these theories? It's not possible, but we do try and interest some of the students sometimes.
Slowly, word by word, click by click, Hawking continues towards a complete theory of the fundamental processes of our cosmos. His theory of everything. His focus now is the very moment of creation, the birth of our universe. But to crack that involves making sense of the least understood force in nature.
My recent experience of weightlessness demonstrates how well we understand gravity on a human scale. But we must understand gravity as it affects individual particles.
Stephen Hawking is like a cosmic crime scene investigator. He's trying to understand something that happened 13.7 billion years ago. The Big Bang. He's turning over all the remnants of the explosion and trying to fit them back together again. The fragments are all the matter and forces of nature we see around us today. But one piece refuses to fit. Gravity. As human beings, we don't notice anything strange about gravity. But if it had been any stronger, the universe as we know it could never have existed. Space would have been pulled back in on itself, obliterating any possibility for planets and stars to form. There are 4 forces in nature, and gravity seems to be strangely weaker than the other 3. As physicist Michio Kaku explains.
We see 4 fundamental forces of the universe today. Gravity, which holds the Earth, the Sun, and the solar system together. The electromagnetic force, which lights up our cities and the internet and laser beams. And also the 2 nuclear forces. But why should there be 4 fundamental forces? We think that at the instant of creation, these 4 forces meld together into a single force, a superforce.
At the Big Bang, everything was one. But as the universe cooled, 4 forces emerged. Electromagnetism and the 2 nuclear forces, which control atoms and radioactivity, all seem to be about the same strength. But the 4th force, gravity, isn't just a bit weaker, it's vastly weaker. As Professor Lisa Randall of Harvard University demonstrates, the electromagnetic forces in a tiny magnet can easily overwhelm a mountain range.
It turns out that gravity is many, many orders of magnitude weaker than the other forces. And certainly gravity doesn't seem that weak when you're climbing up a mountain. But with an incredibly tiny magnet, I can pick up this paperclip with the tiny magnet. Now, is that amazing? Well, this tiny magnet is competing against the gravitational force of the entire Earth. At a fundamental level, the force of gravity is much weaker than the other forces. But the problem is that we don't understand where this huge discrepancy comes from.
And it's this discrepancy that's stopping Hawking achieving his dream. He can't create a theory of everything until he can explain what happened to gravity at the moment of the Big Bang, when the universe was tiny.
If we want to know what happened when the universe began, we have to have a theory that can describe gravity on a very small scale.
Hawking has struggled for decades to solve this problem. But now he is in a race. The final breakthrough may well come from someone else.
Physicists love to explain how our universe arose and how it works. We understand enormous amounts. But when asked how did it all come to be, we don't have one single answer yet.
In 1988, Stephen Hawking's book, A Brief History of Time, was published. Few expected it to be such a runaway success.
I remember reading the draft of his book on a train journey to Beijing, and well, to be honest, when I read the book, I certainly did not anticipate that it was going to be the bestseller it really was.
Overnight, Hawking became a household name. He was in great demand.
Now, my first guest tonight's a truly remarkable man, regarded by many as a genius, Professor Stephen Hawking.
But the pressure of fame took its toll on his marriage. Hawking had set out to write a book that would carry his message to a wider audience and make him a bit of cash to help pay for the expensive specialist care he needed. but he never anticipated the upset it would cause in his personal life. After years of caring for Hawking alone, his wife Jane suddenly found herself surrounded by nurses and assistants. In an interview in 2000, Hawking's youngest son Timothy recalled how, when he was 9 years old, his life was turned upside down.
You know, it just changed things completely. You know, had a lot of new people coming in to the house, wandering in and out. You know, the front door was always open. I think my mum found it hard because nurses started treating our house as their own home. You know, taking baths, helping themselves to food, and you know, our sort of house was turning into a hospital. It started to unsettle the balance of the family. Suddenly, my dad seemed to become a lot more outgoing with people outside the house. He was starting to let his hair down in some ways. He started buying Beatles CDs and stuff, and you know, having parties. In fact, he could also, of course, be more independent now that he had his nurses, and that actually made his life easier, which meant that he didn't really have to be with my mum 24 hours a day.
2 years after his book's publication, Hawking and his wife Jane were separated. In 1995, he married his nurse, Elaine Mason.
I'm marrying the woman I love.
And the world waited eagerly for his much-vaunted theory of everything.
When The Brief History of Time first came out, I think physicists were fairly hopeful that we would have this final theory of everything, maybe within just a few decades.
In 1988, there was certainly cause for optimism. Only gravity had to be explained and brought into the fold. Back in the 1970s, Hawking had already given physics an inkling of how it might work.
By applying quantum mechanics to the edge of the black holes in the 1970s, I was able to revolutionize our understanding of them.
Hawking had proved it was possible to unite the theories of the very large, stars, planets, and gravity, as originally proposed in Einstein's theory of relativity, and blend in some of the theory of the very tiny, of atoms, quantum mechanics.
To expand our understanding further, we need to bring quantum mechanics into the heart of the black hole.
By joining the theories of the large and the tiny in a limited way, Hawking had utterly changed our picture of black holes. He showed they chew up our universe, but then explode, giving off vast amounts of energy and material that eventually forms new stars. Physicists were fascinated. It was as if Hawking had pulled down a wall. Suddenly, the theorists of the very large and the theorists of the very small had something to talk to each other about. If Hawking could find a connection between the large and the tiny in black holes, there must be more. Surely a single theory of the universe could be found that would include how gravity worked, both now and at the universe's beginning. The race was on. Hawking first became enthused about an idea called supersymmetry. Supersymmetry is based on the notion that before the Big Bang, when the universe was just a single point, everything, including gravity, was merged with perfect symmetry into one almighty superforce.
We think that at the instant of creation, there was a superforce, a master force, a single force that governed the properties of this dot-like universe. But then the universe began to expand, and the force cracked.
When the universe began, the superforce was entirely symmetrical. It was made of the same stuff, and it all behaved in the same way. But then as it expanded, this symmetry started to break. In the milliseconds after the Big Bang, forces flew off in all directions, and the universe became messy and uneven. Gravity and all the other parts of nature we see today are the irregular, imperfect descendants of the original symmetry. The theory of supersymmetry solved part of the problem Hawking had with gravity. Now the whole of nature, including gravity, could be unified at the Big Bang by one set of equations. But there was still a problem. If gravity was unified with everything else at the Big Bang, why did it become so very weak afterwards compared to the other forces? The brightest minds, like Hawking and Princeton professor Ed Witten, were trying to work out how the perfection of supersymmetry broke and ended up as the world we see today.
Imagine sitting down at a dinner table. There's a glass to your left, and there's a glass to your right. So the arrangement of the table has a symmetry between left and right, at least for the glasses. It works fine if everybody picks up the glass on the left or if everyone picks up the glass on the right. But a mixture where everybody sits down and ends up with the glass breaks the symmetry. You all pick the glass from the left or the glass from the right. That's an example of what physicists call spontaneous symmetry breaking. And it's ubiquitous in the real world, both for the electrons in a piece of iron and for the early universe settling down from the Big Bang.
Explaining why the universe had settled down the way it had was the next problem Hawking had to solve. Supersymmetry made lots of sense, but there seemed to be no particular reason why gravity should end up so weak. Much work still needed to be done, but Hawking's ability to communicate was slowing down drastically. Today, it is a constant effort.
I'm going to demonstrate using a hand switch, which is what Professor Hawking used to use until about 2 years ago. Now, he uses a menu system which is basically a big screen full of words, and when he presses the switch once, you see this highlighted section that goes up and down. That's actually selecting which part of the screen he wants to speak from. So if you press it and then press it again while it's over the top half, it's now worked out that he wants to say something in the top half of the screen. And if you press it a third time on the right line, it'll go along that line, and a fourth time lets you select a letter. And now we've got a whole screen full of words beginning with Q and R, and you can do the same thing again, and you can select a word. That's how he builds up a sentence, word by word, or if he wants to speak a word that isn't in the list, he can do it letter by letter as well. EIJ is rescaled extrinsic curvature.
Throughout the 90s, at only 4 words a minute, Hawking worked away at the problem of gravity. But cutting-edge physics became increasingly dependent on complex maths, and Hawking was reliant on students and colleagues to perform computations.
Thank you very much.
The next big breakthrough came not from Hawking, but from a colleague just down the corridor in Cambridge. Professor Michael Green is one of the big hitters in what is known as superstring theory, or string theory for short. It suggests that all the particles and forces of nature are actually vibrating little string-like objects. And it seems to magically solve the problem of gravity that Hawking is struggling with.
One of the remarkable things about string theory is that it necessarily includes gravity. And in fact, in the earliest days of string theory, people were trying to formulate a theory which did not include gravity. They didn't understand that string theory necessarily included gravity.
String theory is a radically different way of looking at our universe. In string theory, the entire universe, including space, time, and even gravity, are made up of tiny, string-like objects that only appear to us to be different particles because of the different ways they vibrate. The theory suggests that our world is just a giant mesh of vibrating strings. String theory brings the theories of the very large and the very small together beautifully. Einstein's theory of relativity describes a universe where space bends and curls, just like pieces of string. Quantum mechanics says particles are wavy and fuzzy, a concept well expressed by vibrating strings.
First of all, each vibration of the string corresponds to a particle. Therefore, string theory is a quantum theory. The jumble of particles we see is nothing but the jumble of notes vibrating on a string. But when the string moves in space and time, it forces space and time to curl up. And that's why we have precisely Einstein's equations.
Because string theory can encompass both the tiny quantum world and the vast world of space, it looked like it might hold the answer to the problem of gravity that was so tormenting Hawking. But it was not Hawking who saw the possible solution. It was that chap down the corridor, Michael Green. Here in Aspen, Colorado, he and his colleague John Schwartz finally cracked how to make gravity fit the theory.
We were making progress, we felt, in understanding how string theory or supersymmetrical string theories, which we call superstring theory, but to understand how superstring theory works. But in the early 80s, there was very little interest in our work. People were pursuing other, somewhat related, but other directions. And so we were convinced that what we were doing was quite important, and we found it rather puzzling that there wasn't more interest from our colleagues.
It sort of culminated, as I remember it, essentially in one day when suddenly everything fell, all the pieces of the jigsaw puzzle came together. And it was a really unusual feeling for both of us.
Green and Schwartz had made a huge breakthrough.
When the news came of the Green-Schwartz calculation, that was like a thunderclap. And I was pretty sure life would never be the same again, at least not professional life.
Green and Schwartz's version of string theory not only included gravity, but it had an amazing explanation for why gravity is so weak now. The reason? The universe is made up of 11 dimensions. It may sound like science fiction, but even Stephen Hawking is prepared to admit it might be right.
String theory is the only candidate for a theory of everything that has a certain symmetry that physicists believe in, but have not yet observed. If it is not found, we will have to think again.
Hawking had spent decades leading the quest for a theory of everything. Now someone else had made the vital next step. A great step into a multi-dimensional universe.
During my lifetime, we have discovered many of the laws that govern the universe, but we don't yet understand how they all fit together, or why they seem to be finely adjusted to allow life.
Stephen Hawking has spent 45 years trying to create a theory of everything. His main stumbling block has been finding a way to explain how gravity arose in the white heat of the Big Bang, and why it's so weak. Now the elusive answer seems to have come from elsewhere. String theory has been developed for 20 years now. The latest version is called M-theory, and almost all physicists have huge hope for it as a theory of everything. But to explain gravity's weakness, the theory has to be constructed in 9, 10, even 11 dimensions. It sounds like science fiction, but string theorists believe those extra dimensions to be real. But what does that actually mean?
In string theory, in addition to the 3 space dimensions that we're familiar with, sideways, up and across, there are some extra dimensions. In the simplest versions of the theory, we say there are 6 extra dimensions, which we don't see directly in the physical world. But nevertheless, they could be there.
We can't see the extra dimensions because they are outside our 3D universe. Some could be bigger than our 3 dimensions. Our entire universe could be sitting inside a higher dimension. We could be a bit like fish in a tank, unaware of the world outside, unaware of the extra dimensions.
Today, we physicists believe that we are the fish. We spend all our lives in 3 dimensions, going forward, backward, left, right, and up and down, not realizing that there could be other dimensions, other universes, other ponds, perhaps as many as 11 dimensions in a multiverse of universes. Some people say, well, what's at the edge of the universe? Is there a wall that says the end of the universe? Do not pass go. This is it, folks. The answer is no. Think of the way Columbus handled that question. People said, Columbus, if the earth is round, then what happens when you fall off the edge? And then Columbus said, there is no edge, because you just keep on going around in a circle. So in 2 dimensions, the earth is infinite. You can spend all your time going in a circle. But in 3 dimensions, the earth is a ball. It's finite. In the same way, our universe looks infinite in 3 dimensions. You can go anywhere and there's no wall out there. But in 4 dimensions, in hyperspace, perhaps it's just a pond.
But extra dimensions do not have to be bigger than our 3D universe. Some could be tiny. They could be curled up so small we don't notice them. And that may explain why gravity is so very weak. If Harvard professor Lisa Randall's work is correct.
So it could be that at every point in space, there are these curled up extra dimensions, looking somewhat like these donuts do. Now, it's a little hard to imagine, but the whole idea is that if there are 2 curled up extra dimensions and it's curled up into the shape of a donut, or we call it a torus, there could be one of these donuts at every point in space. And it could be a higher dimensional donut, which is hard to draw and even harder to eat. But it could be that there are even more curled up extra dimensions in this way. And that, but what this illustrates is that at every point in space, we have one of these donuts.
And we may not have seen these extra dimensions because they are too small for us to measure.
Anything else for you? No, thank you.
Physicists now believe that the tiniest, immeasurably small points in space may actually conceal curved up extra dimensions. and that would affect how we perceive gravity. The idea from string theory is that gravity is not weirdly weak after all. It's just that we don't experience it fully. It may be as strong as all the other forces in the universe, but its effects are weakened by having to make its way through extra dimensions. It's a bit like distant music fighting its way through a noisy environment.
Maybe that's why gravity is so weak, because most of gravity flies into hyperspace and disperses, and we only see the remnants. That's why when you hear this music, it's very, very faint, because most of the music is gone in a different direction, and we only hear the remnants.
Extra dimensions act a bit like a shower head. Up close to the tiny extra dimensions, gravity is strong. But as you move away, it gets very weak, very quickly. The final piece in the theory of everything is potentially hovering over the last hole in the jigsaw. The Holy Grail is within reach. If string theory is correct, then gravity is as strong as all the other forces in our universe, but just feels weak because it's fighting its way through extra dimensions. The trouble is, nobody, not even Hawking, has any idea whether any of this is true or not. Supersymmetry, string theory, M theory, extra dimensions, they all exist on paper. There is a little evidence that some of the particles predicted by supersymmetry exist. As yet, there's no hard proof the rest are any more than elegant theories. But we may be standing on the brink of a huge breakthrough.
Particle physics has made fabulous advances in the last 20 years. By colliding particles at the kinds of energies that would have been around at the Big Bang, we have unified 3 of the 4 forces. Gravity still refuses to be tamed. But, perhaps, not for long.
Hawking's optimism in his professional life is matched only by the strength he displays in his personal life. His second marriage to his nurse, Elaine Mason, started to unravel in 2004. For the second time in their 10-year marriage, the police started an investigation into alleged abuse. Members of his nursing staff claimed he had been virtually abandoned outdoors to suffer sunstroke, but claims were met with counterclaims and withdrawals. Throughout, Hawking steadfastly refused to criticize his second wife. However, in late 2006, Hawking filed for divorce. Relations with his first family now seem to have resumed on a normal, civilized basis. Last year, Hawking co-authored a children's book with his daughter Lucy. The subject? Physics, of course. Using physics to explain how our universe came about has been Stephen Hawking's lifelong obsession. String theory might be the answer he seeks. And now, there's an outside chance that we're about to find evidence which will finally tell us how the universe began. At CERN near Geneva in Switzerland, they're building the biggest experiment ever conceived. The Large Hadron Collider works by firing subatomic particles in opposite directions around a 16-mile tunnel. they hit each other at nearly the speed of light. The energies involved replicate the conditions that were around in the early universe. In theory, the machine is not quite powerful enough to explore what gravity was like at the exact moment of the Big Bang. Or is it?
Trying to unify gravity with the other forces in nature would involve an experiment with incredibly high amounts of energy. That would be far beyond the capacity of any machine we have ever built. But if string theory is correct, help may be on hand from extra dimensions.
Amazingly, there is a possibility that we will see extra dimensions at CERN. The evidence for that will be tiny, exploding black holes, something Hawking himself predicted.
So you might ask the question, is it possible that by colliding particles in an accelerator, you could actually produce little black holes?
You might indeed. And the answer is maybe. Black holes can be any size, even as tiny as an atom. If gravity really is seeping into our world through extra dimensions, like water out of a showerhead, then incredible things might happen at CERN. If two particles meet right next to the showerhead where gravity is strongest, they might suddenly form a mini black hole.
Once you get within the distance associated with these extra dimensions, then gravity goes up more fast as distance decreases. And that's what's allowing you to form the black holes more easily.
But Hawking's work on black holes predicts that they would explode very quickly.
And if the black holes were formed in the Large Hadron Collider, they would be very noticeable. It's been said that they would shine like a Christmas tree, and you would be able not only to detect the black holes, you would be able to detect the evaporation of the black hole as predicted by Hawking.
Such a result would be a double whammy. For the first time ever, there would be experimental evidence to back up Hawking's theories about black holes. Hawking might even get a Nobel Prize. And there would be strong evidence that extra dimensions are real, and that string theory is really on the road to a theory of everything.
You would produce extra particles that can travel into the extra dimension. And if we see those particles, it would be strong evidence that these extra dimensions actually exist.
The big switch on at the Large Hadron Collider is waited for with bated breath by the whole of physics. It might well fundamentally change our view of our universe and shed light on the big questions that Hawking has always sought answers to. For Stephen Hawking, it will be yet another reminder of our true place in the vast cosmos.
We once thought we were at the center of the universe. Then we thought the sun was. Eventually we realized we were just on the edge of one of billions of galaxies. Soon we may have to humbly accept that our 3D universe is just one of many multi-dimensional worlds.
So after a lifetime of trying to answer the big questions about existence, what does the universe look like to Stephen Hawking?
Can we now say where we came from and where we are going? I am tempted to say that science is about ever-expanding horizons, and that new discoveries only help us to frame questions in more and more accurate ways. However, there is more to the answer than that.
Stephen Hawking is dogged in his determination. He has lived 45 years longer than his doctors predicted. He may soon lose the use of his vital facial muscles and become totally paralyzed. None of it seems to faze him.
I think Stephen faces in his thoughts absolutely every scenario he could possibly face. He's not afraid of any scenarios, really. I mean, he's an incredibly brave person and a huge risk taker. You know, he's got a really incredible appetite for life.
Just about the only area in his life where Hawking is a stick in the mud is his world-famous voice. It's a voice that was cobbled together from a 1980s telephone answering system.
The card was actually first designed for a sort of automated telephone use. This was back in the 1980s when that was a really, really difficult thing to do. And it was a cutting-edge synthesizer at the time.
Can you finish in 10 minutes?
In 10 minutes. He could have a voice that is more realistic, more easy to understand, and would use less power and wouldn't break so often. But the one he has is recognized all over the world, and it's the one he wants to keep.
Thank you very much.
So what does the universe look like to Stephen Hawking? Remarkably, he's one of the few scientists who've tried to do more than compute what happened at the Big Bang and how it evolved afterwards. He's proposed why the Big Bang happened in the first place.
The universe is governed by two kinds of laws. Laws of evolution, which determine how the universe develops in time, given its state at one time, and boundary conditions, which determine the initial state. So far, almost all scientific effort has been devoted to finding laws of evolution, but Jim Hartle and I proposed the no-boundary condition as the only reasonable initial condition for the universe.
Hawking's no-boundary condition is his most radical suggestion to date. It's a proposal, not a theory, but it is based on strong science. Hawking's universe did not have a beginning, but bizarrely, it has also not existed forever. The best analogy Hawking can give is that of bubbles, but without the man to blow them up. Hawking thinks that the universe spontaneously arises. Time begins when the universe begins. It goes on expanding, perhaps forever. In Hawking's mind, our universe has no creator. It came out of nothing and exists all on its own. It's the ultimate free lunch. Although Hawking did think of making some cash out of it.
Maybe Hartle and I should have patented our idea and have charged everyone royalties for their existence.
And interestingly, many within physics are coming round to Hawking's radical view. Within the 11 dimensions of string theory, some scientists think our universe could be just one of many 3D blobs. In string theory, it's possible that there may exist entirely separate giant sheets of space. String theorists call them membranes, or brains for short, and suggest that 3D universes can form on them. This is where we reach the end of our understanding. And now, even the world's greatest physicists start guessing.
It could be that matter, stuff we know about, is actually stuck or lives on the surface of a brain.
And the idea that we are stuck to one of many membranes raises the distinct possibility that membranes may clash out there in the greater universe.
If we are just one brain, maybe there are many other brains.
There could be other brains elsewhere which we're unaware of.
And so each of these brains would in some sense correspond to a different universe, and maybe these brains would even occasionally collide.
One of the ideas that's been proposed is that the Big Bang explosion 14 billion years ago originated as a collision of brains.
Not only is it possible to make such a theory, but it's got some attractive features, because it can explain why gravity appears to be so weak.
It's all pretty heady stuff. It's the kind of thing physicists dream about. And it's all a long way off being proven. But for Hawking, it's the search that gives his life meaning.
During my lifetime, we have discovered many of the laws that govern the universe, but we don't yet understand how they all fit together, or why they seem to be finely adjusted to allow life. I am confident that we will resolve these mysteries, and I think the years ahead will be a golden age of discovery.
Stephen Hawking may not have single-handedly created a theory of everything, but he's come within a whisker. He may be almost completely paralyzed, but that hasn't stopped him being a tireless explorer. Soon, this master of the universe will be off on his travels again. Hawking plans to be on the first commercial flight out into space. As always, there's a reason for his adventure.
I think we are acting with reckless indifference to our future on planet Earth. At the moment, we have nowhere else to go, but in the long run, the human race shouldn't have all its eggs in one basket, or on one planet. I just hope we can avoid dropping the basket until then.